There is a moon in this solar system that orbits the wrong way. Every other large moon, every single one, orbits in the same direction as its planet spins. This is not a coincidence. It is physics. When a solar system forms, the gas and dust spinning around a young star all rotate in the same direction. The planet inherits that rotation. The moons that form alongside it inherit it too. Everything moves together. Everything. Except Triton. Triton orbits Neptune backwards. Not slightly off. Not tilted at an angle that could be explained away. Completely, unmistakably, nigh, defiantly backwards. And because of that single fact, that one orbital direction, Triton is condemned. The same gravitational interaction that slowly pushes a normal moon outward, giving it more distance, more safety, more time, works in reverse on Triton. It pulls Triton inward, millimeter by millimeter, year by year, orbit by orbit, closer and closer to Neptune, until in 3.6 billion years, it crosses the Roche limit. The point at which Neptune's tidal forces become stronger than the gravity holding Triton together. And on that day, Triton will be destroyed, torn apart, shredded into billions of fragments that will spread into a ring around Neptune, brighter and wider than anything Saturn currently possesses. And then, over millions of years, those fragments will spiral inward and fall into the planet itself. Triton will be gone, as though it never existed. This is already happening. The countdown began the moment Neptune captured Triton 4 billion years ago, and it cannot be stopped. But here is what makes Triton's story one of the most extraordinary in the entire solar system. It is not a quiet world sitting passively in its doomed orbit. Right now, at this very moment, geysers of nitrogen gas are erupting from its surface, rising 8 kilometers into a thin, cold atmosphere before being caught by winds and blown sideways in dark streaks across the ice. Its surface is younger than the first flowering plants on Earth, reshaped by geological forces that should not exist on a world this cold and this far from the sun. It has cryovolcanic plains larger than Spain. It has terrain unlike anything seen anywhere else in the solar system. Vast fields of ovoid depressions that look exactly like the skin of a cantaloupe melon, whose origin is still debated. And beneath all of that geological activity, beneath the erupting geysers and the young resurfaced plains and the strange textured landscape, there may be an ocean. Liquid water at 4.5 billion kilometers from the sun, on a moon that does not belong here, on a moon that is falling toward its destruction, on a moon that has only ever been visited once by a single spacecraft for a single day, 36 years ago. Triton is the 7th largest moon in the solar system. It is larger than every known dwarf planet. It reflects 70% of all light that hits it, outshining Neptune itself in images from the James Webb Space Telescope. It has a thin nitrogen atmosphere. It has seasons so extreme that one pole faces the sun continuously for over 80 Earth years at a time. And it came from somewhere else entirely, from the same distant region of the solar system where Pluto was born, before Neptune reached out and pulled it into a captivity it has never escaped. Tonight, this documentary will take you to the edge of the solar system, or Triton. We will trace Triton's journey from its true home in the Kuiper Belt, through the catastrophic capture that changed everything about it, to the erupting geysers on its surface right now. We will ask whether life could exist in an ocean buried beneath billions of tons of ice, on a world being slowly pulled apart by the planet above it. We will explore the missions that were designed to answer these questions, and why none of them have launched. And we will sit with the mathematics of the countdown, 3.6 billion years, and ask what it means that one of the most geologically active and potentially habitable worlds in the solar system is already condemned. Stay until Chapter 5. Because what scientists have recently discovered about what lies beneath Triton's surface changes the conversation about where life might exist in this solar system entirely. If this documentary moves you, if Triton's story stirs something in you, please consider subscribing. This channel exists to bring the most extraordinary corners of the cosmos into sharp focus. And Triton. 1846, just 17 days after Neptune itself was discovered, a British astronomer named William Lassell pointed his telescope at the newly found planet and saw something moving. A point of light, orbiting Neptune. He had found a moon. He named it Triton, after the Greek sea god, son of Poseidon, whose Roman equivalent is Neptune. The name felt appropriate. A son of the sea god, orbiting the sea god's planet. What Lassell could not have known, and what would not be confirmed for another century, was that this moon was one of the strangest objects in the solar system. Not because of its size, not because of its distance, but because of the direction it was moving. Triton orbits Neptune backwards. In the language of astronomy, its orbit is retrograde. It revolves around Neptune in the opposite direction to Neptune's own rotation. Neptune spins counterclockwise, and Triton orbits clockwise. If you were watching the Neptune system from above, you would see the planet turning one way and its largest moon moving the other. This should not be possible for a moon this large. Small, irregular moons in distant orbits can sometimes be retrograde. They are usually captured asteroids or other small bodies that wandered too close and got trapped. Jupiter has several retrograde moons. Saturn has a few. Uranus has some. But those are all tiny, dark, lumpy, irregular. Nothing like a world. Triton is 2,710 kilometers across. It is the 7th largest moon in the entire solar system. It is larger than every known dwarf planet, including Pluto and Eris. It is massive enough that its own gravity has pulled it into a perfect sphere. It has a thin but real atmosphere. It has weather, of a kind. It has active geological processes reshaping its surface right now. And it is orbiting its planet completely backwards. There is no explanation for this that does not involve Triton arriving from somewhere else. A moon this large simply cannot form in a retrograde orbit. The mathematics of solar system formation do not allow it. When a planet forms, it is surrounded by a disk of material spinning in the same direction as the planet itself. Moons that coalesce from that disk inherit that direction. They orbit prograde in the same direction as everything else. Always, without exception, unless something disrupts the system from outside. Triton was not born here. It is a visitor. A world that formed somewhere else in the solar system, moved through space on its own trajectory for hundreds of millions of years, and then had the extraordinary misfortune, or fortune, depending on your perspective, of coming close enough to Neptune to be captured, pulled from its original path, locked into a new orbit, going the wrong way, forever. The capture happened roughly 4 billion years ago, in the violent, chaotic early solar system when the giant planets were still migrating to their current positions. At that time, The outer solar system was full of large, icy bodies moving on unstable trajectories. Jostled by the gravitational reshuffling of Jupiter, Saturn, Uranus, and Neptune as they found their final orbital configurations. Triton was one of those bodies. It was, almost certainly, a Kuiper Belt object. A distant, icy world, similar in composition and origin to Pluto. In 2024, a study of the chemical compositions of both Triton and Pluto confirmed what scientists had long suspected. The two worlds share the same chemical fingerprints, the same proportions of nitrogen, methane, and carbon monoxide, the same ratios that indicate formation beyond the frost line, in the cold outer reaches of the early solar nebula. Triton and Pluto are siblings, born in the same region of the solar system, shaped by the same early conditions, and then separated, Pluto staying in the Kuiper Belt, Triton being torn away by whatever series of gravitational encounters brought it close enough to Neptune for capture to occur. The precise mechanism of that capture is still debated. Gravitational capture of a large body is not straightforward. For one object to capture another, energy must be lost from the system at exactly the right moment. Otherwise, the incoming body simply passes through, swinging around the planet and continuing on its way. The most compelling theory involves Triton arriving not alone, but as part of a binary system. Like Pluto and its large moon Charon, Triton may have had a companion world of its own. Two objects orbiting each other as they moved through the outer solar system together. When this binary pair came close to Neptune, the planet's gravity interacted with both objects simultaneously. The energy of the interaction was distributed unevenly. Triton was slowed and pulled into a bound orbit around Neptune. Its companion was flung away, ejected into the outer solar system at high velocity, never to be seen again. In this model, Triton's companion essentially sacrificed itself. It gave up its orbital energy so that Triton could be captured. A cosmic severance. Two worlds that had traveled together for hundreds of millions of years, torn apart in a single gravitational encounter. And what followed the capture was, by any measure, catastrophic. When Triton first entered Neptune's gravitational field, its orbit was not the nearly circular path it follows today. It was a wild, highly elliptical orbit, swinging close to Neptune and then far away, the signature of a body that had just been pulled violently from one trajectory into another. Every time Triton passed close to Neptune on that elliptical orbit, tidal forces squeezed and flexed its interior. The same phenomenon that heats Jupiter's moon, Io, today. The most volcanically active body in the solar system. Triton experienced that tidal flexing, but with the added violence of a newly captured orbit. The energy deposited into Triton's interior during those early elliptical orbits was enormous. Enormous enough, according to thermal models, to have kept the entire interior of Triton liquid for at least 1 billion years. For 1 billion years after its capture, Triton was not an icy moon. It was a global ocean, a liquid world, warmer than any ice moon has any right to be. Heated from within by the tidal forces of its captor. Over time, as the orbit circularized through the same tidal interactions that generated that heat, the flexing diminished. The orbit became rounder. The heating reduced. The surface began to freeze. The world we see today, with its icy crust and its thin atmosphere and its erupting geysers, is Triton after cooling. Triton after 1 billion years of liquid interior. Triton after a billion years of potential chemistry, of warm water in contact with rock, of conditions that scientists consider among the most promising in the solar system for the emergence of life. And here is what the data tells us: that cooling may not be complete. The tidal heating has diminished, but radiogenic heating continues. Radioactive elements in Triton's rocky core are decaying, releasing heat, as they have been doing since Triton first formed billions of years ago. Combined with residual tidal energy, thermal models suggest that some portion of Triton's interior may still be liquid today. Not a global ocean, not the 1,000-kilometer deep liquid world of Triton's early history, but a layer, a subsurface ocean, perhaps ammonia-rich, perhaps connecting to the geological activity we see at the surface, hidden beneath an icy crust of unknown thickness. No spacecraft has confirmed this. The only close visit in history, Voyager 2's flyby on August 25, 1989, lasted less than a day at close range and covered only 40% of Triton's surface. Everything we know about Triton's interior is inferred from that brief glimpse and from decades of telescopic observation since. But what Voyager 2 showed, in that single extraordinary day, was a world so geologically active that the entire scientific understanding of what was possible on a cold outer solar system moon had to be revised. Triton is the wrong moon, orbiting the wrong way, around a planet it was never meant to live beside, carrying the heat of its traumatic capture somewhere inside it. Still, and on its surface, as Voyager 2 confirmed, something extraordinary is happening. Something that was the biggest surprise of the entire outer solar system mission. Something that is still happening, right now. Triton is erupting. And that discovery, what Voyager 2 found when it finally arrived, is the story of the next chapter. Equal sign, 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 equal sign. Chapter 2. The capture. Equal sign, 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 equal sign. 4 billion years ago, the solar system was not the orderly, predictable place it appears to be today. The 8 planets were not in their current positions. The Kuiper Belt had not yet settled into its present configuration. The region beyond Neptune was crowded, packed with icy bodies of all sizes, moving on unstable trajectories, colliding, merging, and scattering in response to the gravitational reshuffling of the giant planets as they migrated outward from their original positions closer to the Sun. This period, which planetary scientists call the Late Heavy Bombardment or the Grand Tack, depending on which model you favor, was the most violent era in the history of our solar system. Worlds were being ejected. Orbits were being destabilized. Bodies that had formed in one part of the solar system were being flung into completely different regions by gravitational interactions they had no way to resist. It was into this chaos that Triton's story properly begins. At that time, Triton was not a moon. It was a free object, a world in its own right, orbiting the sun independently, moving through the outer solar system on its own trajectory. Based on the chemical analysis published in 2024, comparing the surface compositions of Triton and Pluto using data from multiple telescopes, both worlds share an unmistakable chemical signature: nitrogen ice, methane ice, carbon monoxide, in proportions that indicate formation in the same region of the outer solar nebula, beyond the frost line, where these volatile compounds could condense and accumulate into solid bodies. The lead author of that study put it plainly. For some reason, Triton was ejected from this region and ensnared by Neptune. They had to have formed beyond the water ice line, which is why Triton and Pluto share the same amounts of the same key elements. One stayed where it formed. The other did not. The question of precisely how Triton was captured has occupied planetary scientists for decades. Simple gravitational capture of a large body is, in the language of orbital mechanics, extremely difficult. When one object passes close to another, their gravitational interaction produces a hyperbolic encounter. The incoming object is deflected, its trajectory bent, but it retains enough energy to escape. For capture to occur, energy must be removed from the system at precisely the right moment. Without that energy loss, Triton would have swung around Neptune and continued on its way, just another Kuiper Belt object passing through. So where did the energy go? The binary capture theory, first proposed in 2006 in the journal Nature, offers the most compelling answer. It begins with a simple observation about the outer solar system. Binary objects, two bodies orbiting each other as they travel through space, are remarkably common among Kuiper Belt objects. Pluto and Charon are the most famous example. But there are dozens of known binary Kuiper Belt objects, pairs of worlds moving together through the outer solar system, bound to each other by their mutual gravity. Triton, the theory proposes, was once part of such a pair. It had a companion, a world of comparable size, perhaps similar to Charon in relation to Pluto, orbiting Triton as the two of them traveled together through the outer solar system. When this binary pair approached Neptune, the planet's enormous gravitational field did not interact with Triton and its companion equally. The geometry of the encounter mattered. Depending on the exact trajectory, the exact angle and velocity at which the pair approached, Neptune's gravity could effectively peel the two objects apart, pulling one inward, slowing it, stealing its energy, while the other was flung outward at high velocity. The energy that Triton lost, the energy that allowed Neptune to hold on to it, was given to the companion. The companion escaped. Triton did not. In a single encounter, perhaps lasting only hours, a world that had been Triton's constant companion for hundreds of millions of years was gone, flung into the outer solar system, or perhaps ejected from the solar system entirely, into interstellar space, where it may still be traveling today. We will never know. There is no way to trace it. The companion is gone, unnamed, unknown, sacrificed to the mathematics of orbital mechanics 4 billion years ago. And Triton, suddenly alone, found itself in a new orbit around a planet it had never been near before. That orbit was nothing like the nearly circular path it follows today. A freshly captured orbit is wild, highly elliptical, swinging the captured body close to the planet at periapsis and then far away at apoapsis. On each close pass, Neptune's tidal forces reached into Triton's interior. The near side of Triton, the side facing Neptune, was pulled more strongly than the far side. This differential pull, stronger on one side than the other, physically deformed Triton, stretched it, compressed it, flexed it. And that flexing, happening repeatedly on every close pass, generated heat. Not surface heat, not warmth from the distant sun, but heat generated inside the rock and ice of Triton's body by the mechanical work of being repeatedly deformed by gravity. The same phenomenon heats Io, Jupiter's innermost large moon, to the point where it is the most volcanically active body in the solar system. For Triton, the tidal heating during its early captured orbit was far more intense than anything Io experiences today. The orbit was highly elliptical, meaning the difference in gravitational pull between Triton's near and far sides was extreme on each close pass. And our thermal models that attempt to calculate the energy deposited into Triton's interior during this period produce extraordinary results. Enough heat was generated, by tidal flexing alone, to melt Triton's entire interior. Not partially, completely. For a period of at least 1 billion years, possibly considerably longer. Triton was not the frozen icy world we see today. It was an ocean world, a global liquid interior kept warm by the relentless mechanical energy of Neptune's tidal forces, covered by a crust of ice that would have been far thinner than what exists today. Think about what that environment would have looked like. In liquid water, or more precisely, a mixture of liquid water and ammonia, which acts as an antifreeze and depresses the freezing point, in direct contact with Triton's rocky core. Mineral-rich, chemically active, with a heat source driving circulation through the liquid, carrying material from the warm, rocky interior up toward the cold, icy ceiling above. This is precisely the environment that scientists believe gave rise to life on Earth. Hydrothermal circulation, warm water rising through cracks in rock, carrying dissolved minerals and chemical energy, meeting cooler water above. The chemistry of life, according to the current leading hypothesis, began at exactly such a boundary. At hydrothermal vents on the early ocean floor, where mineral-rich warm water met colder seawater, and the resulting chemical gradients provided the energy for the first self-replicating molecules. Triton, for at least 1 billion years, had those conditions. Over time, as the tidal interactions gradually circularized Triton's orbit, the close passes became less extreme. The differential pull between the near and far sides decreased as the orbit became rounder. The tidal heating diminished. The interior began to cool. Ice crystallized out of the cooling liquid. Heavy rock and metals settled toward the center. Lighter ice rose toward the surface, and the world stratified into the layered structure planetary scientists believe it has today. Rocky metallic core at the center, possible liquid layer above it, thick ice shell covering everything, and on top of all of that, the complex, geologically young surface that Voyager 2 revealed in 1989. But here is the critical question that those thermal models cannot definitively answer. Is the cooling complete? Radiogenic heating, the slow decay of radioactive elements embedded in Triton's rocky core, continues regardless of what the tidal forces are doing. Uranium, thorium, potassium-40, and these elements have been releasing heat inside Triton since the moment it formed, and they will continue doing so for billions of years into the future. When both radiogenic heating and residual tidal heating are included in thermal models, Many of those models produce a world that still has a liquid layer. Not a global ocean, not the vast, warm sea of Triton's early history, but a shell of liquid water and ammonia, perhaps tens of kilometers thick, sandwiched between the warm, rocky core below and the cold ice crust above. This is not confirmed. No instrument has directly detected it. The only spacecraft to visit Triton, Voyager 2, was not equipped to measure it. The ocean, if it exists, remains hidden, inferred from physics and chemistry, suspected but unproven, waiting for a spacecraft that has not yet been built. What is not hidden, what Voyager 2 confirmed beyond any doubt, is that Triton's surface is extraordinarily, confusingly, beautifully alive. Its surface has been completely reshaped within the last 100 million years, a number so recent, in geological terms, that it corresponds to the age of the Rocky Mountains on Earth. And the agent of that resurfacing, the geological engine driving the activity, is something that had never been seen anywhere in the solar system before Voyager 2 arrived. Triton is erupting. Not with lava. Not with the molten rock that drives volcanoes on Earth or Io. With something colder. Something stranger. Something that, when Voyager 2 first photographed it, made the scientists in the control room stop and look at each other. That discovery, what was rising from Triton's surface in dark plumes 8 kilometers high, is what we explore next. August 25th, 1989. Voyager 2 had been traveling for 12 years. Launched in August of 1977. It had already flown past Jupiter, Saturn, and Uranus, delivering extraordinary images of each system before continuing outward into the dark. Neptune was its final destination, the last planet. And because of the geometry of Neptune's position relative to the Sun, and the impossibility of slowing the spacecraft down for an orbital insertion at this distance, Voyager 2 would have only one chance. A single flyby. Hours of close observation. Then past Neptune, past Triton, and out of the solar system forever. The scientists who designed the Triton flyby trajectory had made a deliberate choice. They could have used the gravitational interaction with Neptune to redirect Voyager 2 toward the ecliptic plane, keeping the spacecraft in the solar system longer and allowing further observations. Instead, they chose to fly close to Triton, close enough to image its surface in detail, close enough to sample its thin atmosphere, close enough to answer, or at least begin to answer, the question of what this backwards orbiting world actually was. The cost of that choice was that Voyager 2 was redirected out of the ecliptic plane entirely, sent on a trajectory that would carry it above and below the solar system, making further planetary flybys impossible. The scientists chose Triton. They gave up everything else for one look at this strange captured moon. And what Voyager 2 showed them, in those hours of close approach, exceeded everything they had anticipated. The first surprise was the surface itself. Voyager 2's cameras revealed a world covered in bright pinkish-white nitrogen and methane ice, with a complex patchwork of terrain types unlike anything previously seen in the solar system. There were smooth plains. There were ridges and faults cutting across the surface in long, curving lines. There were depressions, hundreds of them, roughly circular 30 to 40 kilometers across, distributed across enormous areas of the surface with an eerie regularity. These depressions were not impact craters. Impact craters come in a range of sizes, small, medium, large, distributed randomly across a surface according to the population of impactors that have hit over geological time. These depressions were all roughly the same size, all with smooth, curved walls, all arranged in a pattern that looked, to the scientists studying the images, exactly like the surface texture of a cantaloupe melon. The informal name stuck immediately: cantaloupe terrain. And it covered enormous areas of Triton's surface, particularly in a region now designated Bubembe Regio, with a uniformity and strangeness that had no parallel anywhere else in the solar system. Nobody had expected this. Nobody had predicted it. The leading hypothesis for its formation involves a process called diapirism, the rising of less dense material through a layer of denser material above it. When a warm, less dense material, ice of a particular composition, is trapped beneath a heavier layer, it does not stay put. It rises, slowly, over geological time, forming upward-moving blobs that press against the overlying material and create rounded surface expressions as they push upward. The same process occurs in Earth's mantle, where hot rock rises through cooler rock in the convection currents that drive plate tectonics. On Triton, the rising material would be warm ice, perhaps ice mixed with ammonia, rising through a denser ice layer above it, creating the rounded depressions visible at the surface as the overlying material bows upward and then collapses. For diapirism to operate at the scale seen on Triton, the interior must be layered. There must be a warm layer below, then a cooler, denser layer above, and there must be a heat source driving the warm material upward. Cantaloupe terrain, in other words, is indirect evidence for internal heat. But the cantaloupe terrain, extraordinary as it was not the biggest surprise. The biggest surprise was in the southern polar cap. Triton's southern pole, the hemisphere facing the sun at the time of Voyager 2's flyby, was covered in a bright cap of nitrogen and methane ice. And across that bright cap, Voyager 2's cameras captured something that made the science team at the Jet Propulsion Laboratory stop mid-sentence during their press briefing. Dark streaks. More than 100 of them. Long, dark, parallel lines painted across the bright southern ice cap, pointing in the same direction, laid down by winds at high altitude blowing consistently from one direction. These were the deposits of eruptions. Dark material, nitrogen gas mixed with dust and fine organic particles, had risen from the surface in plumes, been caught by winds at altitude, and then settled back to the surface kilometers downwind in these characteristic dark streaks. And as Voyager 2 watched, it caught 2 of those eruptions in the act. 2 active plumes rising from Triton's southern polar cap, visible in real time. One of them, designated the Hiley plume, rose 8 kilometers above the surface before being sheared sideways by the wind. 8 kilometers. On a world with a surface gravity only 8% of Earth's, and an atmospheric pressure 70,000 times lower than Earth's. A plume can rise extraordinarily high before the thinning atmosphere loses the ability to support it. The second plume, Mahilani, was shorter but equally unmistakable. Dark, vertical, rising from the surface of a world at minus 235 degrees Celsius and reaching kilometers into the sky above it. Triton was erupting in real time while Voyager 2 watched. The immediate question, the one that has driven Triton research ever since, was what was driving those eruptions. 2 main hypotheses emerged, and they remain in competition today. The first is the solid greenhouse model. In this hypothesis, the eruptions are driven not by internal heat, but by sunlight. Triton's polar cap is covered by a thin layer of transparent nitrogen ice. Ice that is clear enough for sunlight to pass through, like glass. Beneath that transparent layer, there is darker material, ice mixed with organic compounds, that absorbs the sunlight passing through the transparent layer above. The absorbed sunlight warms the dark material beneath, even at minus 235 degrees, even with sunlight 900 times fainter than at Earth, warming it just enough to cause the nitrogen ice immediately below it to sublimate. That gas builds up pressure beneath the transparent lid, building, until it finds a weakness, a crack, a thin point, and erupts through it, carrying the dark material with it, rising into the atmosphere as a plume. This model is supported by the observation that both active plumes Voyager 2 caught were located between 50 and 57 degrees south latitude, precisely the region receiving the most concentrated sunlight during southern summer. CO2 geysers on Mars, driven by the same solid greenhouse mechanism, erupt from the Martian south polar cap each spring in an identical process. The physics is understood. The mechanism is credible. But there is a problem. The estimated output of Triton's plumes is far higher than the solid greenhouse model can easily explain. The two active plumes Voyager 2 observed were estimated to be ejecting between 10 and 400 kilograms of material per second. The upper end of that estimate, 400 kilograms per second, is comparable to the output of Enceladus's cryovolcanic plumes. Enceladus erupts material from its subsurface ocean through cracks in the south polar ice, driven by tidal heating from Saturn's gravity. Its plumes output roughly 200 kilograms per second. It is one of the most actively erupting worlds in the solar system, and Triton may match it, or exceed it. The solid greenhouse model, driven by faint sunlight reaching Neptune, struggles to produce eruption rates at that scale. And so, the second hypothesis remains very much alive. The cryovolcanic model. In this hypothesis, the eruptions are driven not by sunlight, but by internal heat. The warm interior of Triton, whether maintained by radiogenic heating alone or by a combination of radiogenic and residual tidal heating, drives geological activity that reaches the surface. Material from depth, warm, pressurized, finds pathways through the overlying ice and erupts, not as lava, not as molten rock, but as a mixture of water ice, ammonia, and nitrogen. A cryovolcanic eruption, cold lava, chemically similar to what you would expect from a liquid water and ammonia ocean venting through cracks in the overlying ice shell. If the cryovolcanic model is correct, then the plumes of Triton are not just geysers. They are the fingerprints of an ocean, material from a subsurface liquid layer, rising through the ice, erupting into the sky, and falling back to the surface as the dark streaks that Voyager 2 photographed. In that case, every time Triton erupts, it is showing us what lies beneath. The chemistry of the plume material would reflect the chemistry of the source. And if that source is a liquid water ocean, the plume chemistry would carry the signatures of that ocean into the atmosphere, where a future spacecraft equipped with the right instruments could detect them. The cryovolcanic model is also supported by the broader geological evidence from Triton's surface. The cantaloupe terrain, if it formed by diapirism, requires a warm interior driving material upward. The ridge systems on Triton's surface, long linear features cutting across the ice, are structurally similar to the lineae on Europa, the ridges that scientists believe form when Jupiter's tidal forces crack Europa's ice shell and allow material from the subsurface ocean to well up and refreeze. And then there is Leviathan Patera, a massive caldera, a collapse depression formed when a large reservoir of material beneath the surface drains away. Identified on Triton's surface by Voyager 2. Surrounding it, a cryovolcanic plain called Cipango Planum, covering an area of at least 490,000 square kilometers. Larger than Spain. A plain of material that erupted from the interior, flowed across the surface, and froze. And associated with Leviathan Patera, two enormous cryolava lakes, bodies of material that were once molten, that were for a period liquid on Triton's surface, before freezing solid as the eruption ended. These cryolava lakes are significant for a reason that goes beyond their size. If the cryolava was composed primarily of water ice with some ammonia, as the chemistry of Triton's interior strongly suggests, then while those lakes were molten, they were stable bodies of surface liquid water. The first such bodies identified anywhere in the solar system outside of Earth. What all of this geological evidence points to, taken together, is a world whose interior is not the cold, inert, frozen mass that its surface temperature would suggest. Something is producing heat inside Triton. Something is driving material upward, through the ice, to the surface. Something is keeping Triton geologically alive, billions of years after its capture. The surface of Triton is less than 100 million years old. In a solar system 4.5 billion years old, 100 million years is yesterday. Only 179 confirmed impact craters have been found on Triton's entire surface, compared to 835 on Miranda, a moon with only 3% of Triton's surface area. Miranda is old and heavily cratered. Triton is young and almost crater-free. Because Triton's geological engine keeps erasing the evidence of impacts, covering them over with new material from below, resetting the surface again and again. And underneath all of that activity, the question that matters most remains unanswered. Is there an ocean? Is there liquid water, right now, in the darkness beneath Triton's frozen crust? And if there is, has it been there long enough, warm enough, chemically rich enough, that something might have begun? That question, the deepest question Triton raises, is the one we explore in the next chapter. There is a thought experiment that planetary scientists use when they want to communicate the strangeness of the outer solar system. Take everything you know about where liquid water can exist, the temperature range, the pressure requirements, the proximity to a heat source sufficient to maintain it. Apply those constraints to the solar system, and the conclusion is obvious. Liquid water belongs near the sun, but not at Neptune, not 30 astronomical units from the sun, not on a moon with a surface temperature of minus 235 degrees Celsius, not on Triton. Except, as the science of the past 3 decades has made increasingly clear, the thought experiment is wrong. Or rather, it is incomplete. It assumes that the sun is the only heat source available. It ignores the heat that comes from inside, from the decay of radioactive elements, from the flexing of tidal forces, from the residual warmth of a catastrophic capture that kept a world's interior molten for over 1 billion years. The solar system, it turns out, is full of liquid water. It is just not where anyone expected to find it. Europa, Jupiter's icy moon, has a global subsurface ocean estimated to contain twice as much liquid water as all of Earth's oceans combined. Enceladus, Saturn's small, geologically active moon, has an ocean in direct contact with its rocky core, with hydrothermal vents erupting mineral-rich warm water into the liquid above. Ganymede, the largest moon in the solar system, confirmed to have a subsurface ocean by the Hubble Space Telescope in 2015. Callisto, Europa, Titan, Dione, possibly Mimas. The list of confirmed or strongly suspected ocean worlds in the outer solar system has grown from 0 to at least 7 in the space of 3 decades. And Triton, with its geologically young surface, its active eruptions, its tidal heating history, and its rocky core generating radiogenic heat, fits the profile of an ocean world more convincingly than almost any other body on that list. The case begins with what Triton is made of. Density measurements, derived from Voyager 2's gravitational interaction with Triton during the flyby, give a mean density of 2.061 grams per cubic centimeter. Pure water ice has a density of about 0.9 grams per cubic centimeter. Silicate rock, the material that makes up Earth's mantle, has a density of roughly 3 grams per cubic centimeter. Triton's density sits between these two extremes, indicating a body composed of roughly 30 to 45% water ice by mass, with the remainder being rock and metal. A world with that much water, combined with a heat source sufficient to melt it, will have an ocean. The only question is whether the heat source is adequate, and the evidence suggests that it is. Radiogenic heating alone, from the decay of uranium, thorium, and potassium-40 in Triton's rocky core, is estimated to generate enough heat to maintain a liquid layer if the ice shell above is sufficiently insulating. The key variable is the thickness of that ice shell. A thicker shell provides more insulation, trapping more heat from below, keeping the liquid layer warmer. A thinner shell allows more heat to escape, potentially losing enough energy that the liquid layer freezes solid. Current estimates for Triton's ice shell thickness range from a few tens of kilometers to perhaps a few hundred kilometers. But without a spacecraft capable of measuring it directly, the uncertainty is large. What thermal models consistently show, across a wide range of reasonable assumptions about ice shell thickness and core composition, is that some portion of Triton's interior should still be liquid today. Not necessarily a vast, deep ocean, but a layer. A shell of liquid water, perhaps mixed with ammonia, which acts as an antifreeze and depresses the melting point of ice significantly, sandwiched between the warm, rocky interior below and the cold, thick ice crust above. The ammonia is important. Pure water freezes at 0 degrees Celsius under normal conditions. But water mixed with ammonia, in a eutectic mixture, can remain liquid at temperatures as low as minus 97 degrees Celsius. This is not a hypothetical chemistry. Ammonia is present on Triton's surface, detected by spectroscopy, and is expected to be present in its interior as well, incorporated into the ice when Triton formed in the outer solar nebula. An ammonia water ocean inside Triton could persist at temperatures far below the freezing point of pure water, making it far easier for a liquid layer to survive despite the limited heat sources available. But models are models. The question that matters is what is actually down there. And to answer that question, planetary scientists have developed a strategy that has already worked once. At Europa, When the Galileo spacecraft orbited Jupiter in the 1990s and early 2000s, it detected something unexpected in the magnetic field data around Europa. Jupiter has an enormously powerful magnetic field, rotating with the planet and sweeping past Europa on every orbit. When a rotating magnetic field sweeps past a conductive body, it induces a secondary magnetic field in that body. The strength and character of that induced field depends on how conductive the body is. Rock is a poor conductor. Ice is a poor conductor. But salt water, liquid water with dissolved minerals, is an excellent conductor. When Galileo measured the magnetic field around Europa, it found exactly the signature of an induced field, a secondary magnetic response, consistent with a global layer of electrically conductive material inside Europa. The only material that fits, given Europa's composition and interior structure, is a saltwater ocean. That single measurement, magnetic induction, confirmed Europa's ocean more convincingly than any other technique available. The same technique should work at Triton. Neptune has a powerful magnetic field, tilted significantly relative to its rotation axis and offset from the planet's center, which means it sweeps past Triton in a complex, time-varying pattern. If Triton has a subsurface ocean of liquid salt water, Neptune's rotating magnetic field should induce a measurable secondary magnetic field in that ocean. A spacecraft equipped with a sensitive magnetometer, flying close to Triton in a carefully designed orbit, could detect that induced field, or fail to detect it. Either way, the answer would be definitive. Ocean or no ocean. Confirmed or ruled out. Voyager 2 was not equipped to make that measurement. The ocean, if it exists, remains undetected, unconfirmed, waiting. There is another line of evidence that planetary scientists find compelling, though it is indirect. The ridge systems. Voyager 2 imaged extensive networks of ridges on Triton's surface. Long, linear features cutting across the ice in patterns that are structurally similar to features seen on Europa. On Europa, these ridges are called lineae, and the leading hypothesis for their formation involves the ocean below. Jupiter's tidal forces crack Europa's ice shell, opening fissures that reach down to the liquid layer beneath. Ocean material, warm, pressurized, wells up through the crack. It freezes as it contacts the cold surface environment. The crack closes, opens again. More material wells up. The cycle repeats. And gradually, a ridge builds up along the line of the crack, made of refrozen ocean material deposited over thousands of repeated, open-close cycles. Triton's ridges show a similar morphology. If they formed by the same mechanism, then they are not just surface features. They are the visible expression of an ocean below, places where the ice shell cracked and ocean material rose to the surface and froze. Every ridge on Triton, in this interpretation, is a scar left by a moment when the hidden ocean briefly touched the surface world. And then there is the question of the plumes. If the cryovolcanic model for Triton's geysers is correct, if the eruptions are driven by internal heat rather than by solar heating, then the material being erupted is coming from depth, from the warm interior, from, potentially, the ocean itself. The Cassini spacecraft flew through Enceladus's plumes, sampled them directly, and found complex organic chemistry, silica nanoparticles indicating high-temperature water-rock interaction, and molecular hydrogen, all pointing to active hydrothermal vents on Enceladus's ocean floor. If Triton's plumes are cryovolcanic, a future spacecraft flying through them could directly analyze the chemistry of whatever lies beneath the ice. Organic molecules, mineral signatures, perhaps, in the most optimistic scenario, biosignatures, molecules that can only be produced by biological processes. The plumes, if they exist for the right reason, are windows. Not perfect windows, but samples of what the ocean is made of, what chemistry is happening inside it, and whether that chemistry has gone anywhere extraordinary in the billion years it has had to operate. 1 billion years. That is the minimum time that Triton's interior was liquid, kept warm by tidal heating after the capture. Life on Earth took somewhere between a few 100 million and 1 billion years to emerge after the planet formed, in conditions that were also warm water in contact with rock. The timing is not disqualifying. The chemistry is not disqualifying. The energy source is not disqualifying. What is unknown, what keeps the question open rather than answered, is whether life, once it emerges, can persist as the heat source that created its environment slowly diminishes. We have never found life anywhere except Earth. We do not know how common or rare the origin of life is. We do not know whether the conditions on early Triton were sufficient. What we do know, with confidence, is that Triton had the conditions. Liquid water, a heat source, chemistry, time. And what we know with equal confidence is that the only way to find out whether those conditions led anywhere is to go there. But first, there is something else about Triton that demands attention. Something that distinguishes it from every other ocean world candidate in the solar system. Something that adds an urgency, a weight, to the question of whether life exists beneath its ice that no other world quite carries. Triton is dying. Not metaphorically. Not on a timescale so vast it has no meaning. It is dying on a schedule that planetary science can calculate to within a reasonable margin of error. And the countdown, the mathematics of the orbit that is already decaying, is the subject of the next chapter. In the history of solar system exploration, there have been moments when humanity stood at a threshold. When the technology existed, when the trajectory was calculable, when the scientific case was overwhelming, and when the only remaining question was whether the will existed to act on what the science was saying. The decision to send New Horizons to Pluto was one such moment. For decades, Pluto had been a blurry dot, a point of light in even the best telescopic images. New Horizons was proposed, debated, nearly canceled multiple times, and eventually launched in 2006, arriving at Pluto in 2015, with cameras sharp enough to resolve features kilometers across on a world 3 billion miles away. What it revealed: the nitrogen plains, the mountain ranges of water ice, the haze layers in the atmosphere, the extraordinary complexity of a world that everyone had assumed would be simple and dead, transformed Pluto from a curiosity into one of the most scientifically compelling objects in the solar system. Triton deserves the same. And unlike Pluto, where the scientific case for a mission took decades to build into something compelling enough to fund, Triton's case was already strong in the 1990s. Voyager 2 had shown enough, in its single day of close observation, to make clear that Triton was extraordinary. The geysers, the young surface, the cantaloupe terrain, the cryovolcanic plains, the retrograde orbit pointing to a capture origin, the density indicating a large water ice component. All of it, in combination, pointed toward a world that warranted a dedicated mission as urgently as any target in the outer solar system. But Neptune and Triton are very far away. And very far away, in the context of planetary missions, means very expensive, very slow, and very technically demanding. The journey from Earth to Neptune takes approximately 12 to 13 years with current propulsion technology. Even with the gravitational assist of a Jupiter flyby, which provides a crucial velocity boost that dramatically reduces both travel time and fuel requirements. Jupiter flyby opportunities. The windows in which a spacecraft launched from Earth can use Jupiter's gravity to accelerate toward Neptune. Occur at specific intervals, determined by the orbital positions of the two planets. The most favorable window currently being discussed, the one that the planetary science community has identified as the best opportunity in decades, opens in the early to mid-2030s. A spacecraft launched in that window, using a Jupiter gravity assist, could reach Neptune in approximately 12 to 13 years, arriving in the mid-2040s. With enough time to conduct meaningful science before the scientists who designed the mission reach retirement age. If that window is missed, the next comparable opportunity does not arise until the 2040s for launch, meaning arrival in the late 2050s at the earliest. An entire generation of planetary scientists, the ones who have spent their careers building the case for a Neptune and Triton mission, would be gone before their spacecraft arrived. Against this backdrop, in 2019, a team of scientists led by Louise Proctor of the Lunar and Planetary Institute submitted a proposal to NASA's Discovery program. The mission was called Triton. It was elegant in its ambition and disciplined in its constraints. Rather than attempting to enter orbit around Neptune, which would require enormous amounts of fuel and dramatically increase the cost and complexity of the mission, Triton was designed as a flyby, a single close pass of the Triton system, lasting hours, but carefully orchestrated to answer the most critical scientific questions. The mission's primary objective was the ocean. To determine, definitively, whether Triton has a subsurface ocean of liquid water. Triton would have carried a magnetometer capable of detecting the induced magnetic field that a salty conductive ocean would produce in response to Neptune's rotating magnetic field. The same technique that confirmed Europa's ocean via the Galileo spacecraft. Proven, reliable, unambiguous in its interpretation. An ocean, yes or no, from a single close flyby equipped with the right instrument. Triton would also have carried infrared and ultraviolet spectrometers, capable of analyzing the composition of Triton's surface and its thin atmosphere in far greater detail than Voyager 2's instruments allowed. A wide-angle and narrow-angle camera system, capable of imaging Triton's surface at resolutions comparable to the best images New Horizons returned from Pluto, mapping the 60% of the surface that Voyager 2 never saw. And crucially, the trajectory was designed to fly Triton through the plumes, through the active eruptions rising from Triton's southern polar cap. The same strategy that Cassini used at Enceladus, flying directly through the plume material, sampling whatever was being erupted from the interior. If Triton's plumes are cryovolcanic, if they contain ocean material, Triton would have been able to detect the chemical fingerprints of that ocean directly. Organic molecules, mineral signatures, the isotopic ratios that could indicate or rule out biological processing of the material. The total cost of the Triton mission was estimated at approximately $800 million to $1 billion. Within the budget envelope of NASA's Discovery program, which funds medium-class planetary science missions. The science team argued, convincingly, that Trident represented extraordinary value for the cost. A potential ocean world. A potential habitability detection. The first detailed look at an entire class of captured Kuiper Belt objects. The first opportunity to compare Triton directly with Pluto, using modern instruments, and understand how the same type of world evolves differently depending on whether it ends up as a free dwarf planet or a captured moon. A note: Trident was selected as one of 4 finalists in the Discovery Program's 2019 competition. It underwent detailed study. It was evaluated for technical feasibility, scientific merit, cost, and schedule. And in 2021, NASA announced the 2 missions selected from the 4 finalists. Trident was not among them. The 2 selected missions, Defiantly, a probe designed to descend through Venus's atmosphere, and Veritas, an orbital mission to map Venus's surface, were both focused on Venus. Both scientifically justified. Both important. But neither of them will tell us whether Triton has an ocean. The planetary science community's response to Trident's rejection was notably direct. Multiple scientists pointed out that the 2030s launch window was the critical constraint. That if a Neptune and Triton mission was not launched in that decade, the next opportunity would delay the mission by roughly 20 years. Trident was not the only mission concept developed for Triton. The Triton Ocean World Surveyor, a more ambitious concept developed at the Jet Propulsion Laboratory, proposed an orbiter rather than a flyby. A spacecraft capable of entering orbit around Neptune and conducting extended observations of Triton over multiple flybys, accumulating far more data than a single flyby could provide. The Nautilus concept, even more ambitious, proposed an orbiter with a small atmospheric probe capable of entering Neptune's atmosphere while the main spacecraft studied Triton from orbit. None of these missions has been approved. None of them is currently funded. The most recent Planetary Science Decadal Survey ranked a Uranus orbiter as the top priority large mission for the next decade. Uranus, not Neptune. The scientific community understood the decision. It did not mean Neptune and Triton are unimportant. It meant that they are competing for limited resources with many other deserving targets. And in that competition, the additional technical challenge of Neptune's distance costs it priority ranking. But the 2030s window is coming regardless of what decisions are made in the next few years. The planetary positions that create the favorable Jupiter gravity assist trajectory will occur on their own schedule, indifferent to mission selection processes and budget negotiations. The James Webb Space Telescope has provided new data on Triton, its surface reflectivity, its position in the sky, the general character of its infrared spectrum. Future JWST observations will include dedicated spectroscopy of Triton's surface. This is valuable. It is not sufficient. JWST cannot measure the induced magnetic field. JWST cannot fly through the plumes. JWST cannot image the unseen 60% of Triton's surface. JWST cannot tell us whether there is an ocean. Only a spacecraft at Triton, measuring the magnetic field from close range, sampling the plume chemistry directly, imaging the surface at resolution comparable to what New Horizons achieved at Pluto, can do that. And, as of today, no such spacecraft has been approved. No such spacecraft is being built. No such spacecraft has a confirmed launch date. What exists, what the planetary science community has produced over 3 decades of work since Voyager 2's flyby, is the complete scientific case. The models, the mission designs, the instrument specifications, the trajectory calculations, the cost estimates, everything that a decision maker would need to decide to go. The scientific case for Triton is as strong as the scientific case for any target in the outer solar system. A possible ocean world, active geology, in a capture origin connecting it to the broader population of Kuiper Belt objects. A limited window before the orbital opportunity closes for a generation. And a countdown, 3.6 billion years to destruction, that frames the entire story with a weight that no other target in the solar system quite carries. Triton is asking to be visited. Whether that visit happens in the 2040s, or the 2060s, or not at all within any of our lifetimes, depends on decisions being made right now. In budget offices, in priority-setting committees, in the slow, careful, frustrating machinery of how humanity decides what to do with the extraordinary capability it has built to explore the solar system. But Triton, regardless of those decisions, will keep erupting, keep orbiting, keep spiraling, imperceptibly, toward its end. And somewhere beneath its frozen surface, in the darkness that no human instrument has yet been able to pierce, whatever is there, ocean or ice, life or chemistry, will keep doing what it's been doing for 4 billion years, waiting. Not on any planet, not on any moon, not on any asteroid, comet, or dwarf planet that any spacecraft has ever visited. It covers enormous areas of Triton's western hemisphere, spreading across hundreds of thousands of square kilometers of the surface. A terrain so distinctive, so immediately recognizable, that the scientists who first saw it in Voyager 2's images reached for the most ordinary comparison they could find. A piece of fruit. Cantaloupe terrain, named for the North American cantaloupe melon, whose skin is covered in a characteristic pattern of irregular rounded ridges enclosing slightly sunken areas. On Triton, the pattern is rendered at a scale that makes the comparison both apt and staggering. Each individual depression, each cell in the cantaloupe pattern, is roughly 30 to 40 kilometers across. 30 to 40 kilometers. The distance from one side of a major city to the other. Repeated hundreds of times across a surface area larger than Western Europe. And these depressions are not impact craters. The distinction matters. Impact craters come in a range of sizes determined by the size distribution of the impacting objects. Small craters are common. Large craters are rare. The relationship between crater size and frequency follows a predictable statistical distribution that planetary scientists can use to date surfaces by counting craters. An old surface will have many craters of all sizes. A young surface, one recently reshaped by geological activity, will have few. The cantaloupe terrain has almost none. Only 3 probable impact craters have been identified within the entire extent of the cantaloupe terrain. 3. On a surface area that, on an old, geologically inactive world, should have accumulated thousands. And the depressions themselves, the cells of the cantaloupe pattern, are all approximately the same size. 30 to 40 kilometers, with smooth, curved walls, distributed in a pattern that has a regularity, an evenness of spacing, that is completely inconsistent with random impact cratering. Something else made these. Something internal. Something geological. The leading hypothesis, diapirism, begins with a simple physical principle. In any layered material, whether it is the mantle of a rocky planet or the ice shell of a frozen moon, If a less dense layer is trapped beneath a denser layer above it, the system is gravitationally unstable. The less dense material wants to rise. The denser material above it wants to sink. Given enough time and enough heat to allow the materials to deform slowly, the less dense material will begin to move upward in discrete blobs, columns of buoyant material pushing through the overlying denser layer, in a process that geologists call diapirism. The same process operates in Earth's mantle, where hot, less dense rock rises in convection cells while cooler, denser rock sinks, driving the plate tectonic system that reshapes Earth's surface over geological time. On Triton, the diapirs would be composed not of molten rock, but of warm ice, perhaps a mixture of water ice and ammonia, rising through a denser layer of purer water ice above it. As each diapir pushes upward, it bows the overlying layer upward, creating a rounded dome on the surface. Eventually, as the diapir spreads laterally at the base of the overlying layer, the dome collapses slightly, leaving a rounded depression at the surface. The depression is what we see, the cell of the cantaloupe pattern. For this process to operate at the scale visible on Triton, the interior must be warm enough for ice to deform and flow over geological time. It must be layered, with a less dense material below and a denser material above. And the heat source must be sustained, not a brief pulse, but a continuous or long-duration source of warmth driving the convection over millions or tens of millions of years. The cantaloupe terrain, in other words, is a record of Triton's internal heat, a surface expression of the geological engine operating below, and its extreme youth, less than 10 million years old, based on the near total absence of impact craters, means that engine was operating recently, very recently, by geological standards, yesterday. Above this extraordinary surface, Triton has an atmosphere. Thin, extraordinarily thin, but real. Surface pressure approximately 0.015 millibars. For comparison, Earth's surface pressure is 1,013 millibars. Triton's atmosphere is roughly 70,000 times thinner than Earth's. Mars, often described as having a thin atmosphere, has a surface pressure about 500 times greater than Triton's. And yet, in the context of the outer solar system, Triton's atmosphere is significant. It is composed primarily of nitrogen, with trace amounts of carbon monoxide and small quantities of methane near the surface. The same general composition as Pluto's atmosphere. Another piece of evidence for the shared origin of the two worlds. And like Pluto's atmosphere, Triton's is not static. It breathes. Triton's orbit, combined with Neptune's own orbital motion around the Sun, subjects Triton to seasons of extraordinary duration and intensity. Neptune takes 165 Earth years to orbit the Sun. Triton's orbital plane is tilted significantly relative to Neptune's orbit, meaning that as Neptune moves around the Sun, the angle at which sunlight hits Triton's poles changes dramatically over the course of a Neptunian year. The result is a seasonal cycle in which one of Triton's poles faces the Sun continuously for approximately 82 Earth years, receiving prolonged, uninterrupted sunlight, before the geometry shifts and the other pole begins its own 82-year period of illumination. During the sunlit period, nitrogen and methane ice in the polar cap that faces the Sun begins to sublimate, transitioning from solid to gas, adding material to the atmosphere and slightly increasing its pressure. During the dark period, when that pole loses its sunlight, the atmosphere in that region begins to freeze back out, falling as frost onto the polar surface, slightly reducing the atmospheric pressure. The atmosphere of Triton is a seasonal phenomenon, waxing and waning over an 82-year cycle, redistributing nitrogen and methane between the surface and the sky on a timescale longer than a human lifetime. When Voyager 2 flew past Triton in 1989, it was near the peak of Triton's southern summer. Today, decades later, Triton's seasonal geometry has shifted. The northern hemisphere is receiving more sunlight than it was in 1989. The patterns of frost deposition and sublimation, the locations of the most active geological features, may have shifted accordingly. A spacecraft visiting Triton today would see a different seasonal face than the one Voyager 2 recorded. A world in a different moment of its long, slow, seasonal cycle. And above all of this, above the cantaloupe terrain and the seasonal atmosphere and the erupting geysers, hanging in Triton's black sky, is Neptune. If you stood on Triton's surface, in the hemisphere that permanently faces Neptune, you would see something that no human has ever seen from any surface in the solar system. Neptune, hanging motionless in the sky. Because Triton is tidally locked to Neptune, it always presents the same face toward the planet. And from the Neptune-facing hemisphere, the planet never rises and never sets. It simply hangs there, enormous, blue, filling approximately 8 degrees of sky, 16 times the angular diameter of the full moon seen from Earth. Neptune, at 8 degrees of apparent diameter, is not a dot. It is a disk, a visible, detailed sphere, with cloud features moving across its surface, storms rotating through its atmosphere, the faint dark arcs of its ring system perhaps barely visible at the planet's edges. A world hanging overhead, filling the sky the way no planet fills the sky from any other large moon in the solar system. And surrounding that blue disk, the stars. More stars than any human eye has ever seen, undimmed by atmosphere, unsoftened by moisture or dust. The Milky Way, a dense, brilliant river of light across the perfect black. And on the horizon, if you look toward the south, the faint dark streaks of the most recent geyser eruptions settling downwind across the bright polar ice. Dark nitrogen dust drifting in a wind too thin to feel, laying down another dark streak, another record of another eruption, on a surface that has been accumulating those records for longer than complex life has existed on Earth. This is Triton, a world of extraordinary contrasts. Ancient capture, recent surface, extreme cold, internal warmth, alien landscape, familiar geological processes, doomed orbit, vigorous activity. World that does not behave the way a world at this distance from the sun has any right to behave. A world that keeps surprising every model built to describe it. A world that, with every new piece of data, gives scientists more reasons to believe that what lies beneath its frozen surface matters. And in the final chapter, we bring all of it together. Not just what Triton is, but what it means. What a world like this, captured, erupting, possibly alive, certainly doomed, tells us about the solar system we live in, about the places life might exist, about the questions that remain open, and about the extraordinary privilege of living in the moment, this specific moment in history, when we know enough to ask the right questions and still have time to go and find the answers. The encounter lasted less than a day at close range. Voyager 2 had been in space for 12 years at that point. It had already transformed our understanding of Jupiter, Saturn, and Uranus, delivering images and data from each system that overturned assumptions and revealed complexities that no Earth-based telescope had been able to detect. And now, at the outermost planet, it spent its final hours of close planetary science on Triton, not on Neptune, on its captured moon. The scientists who made that choice, who sacrificed the ability to redirect Voyager 2 for further exploration in order to fly close to Triton, understood something that the data subsequently confirmed. Triton was the more interesting target. Neptune was a planet, large, distant, predictable in its broad strokes. Triton was an anomaly, a world that should not be where it was, orbiting the wrong way, covered in young ice, with a density suggesting a large water component and a capture history suggesting a violent thermal past. The scientists who pointed Voyager 2's cameras at Triton were betting that anomalies are where the interesting science lives. They were right. What Triton revealed in that single day of close observation, and what subsequent decades of telescopic study and theoretical modeling have added to that foundation, amounts to one of the most complete arguments in planetary science for a specific, testable hypothesis. The hypothesis is this: liquid water, and the chemistry that liquid water enables, is not confined to the inner solar system. It is not confined to worlds warmed by the sun. It exists, right now, in the deep interiors of worlds scattered across the outer solar system. Worlds kept liquid not by sunlight, but by the heat of their own interiors, by tidal forces and radioactive decay and the residual warmth of violent histories. Europa, Enceladus, Ganymede, Titan, Triton, possibly Eris, possibly dozens of others in the Kuiper Belt whose interiors have never been studied closely enough to know. The solar system is not a thin, habitable shell around a warm star, with life possible only in the narrow band where sunlight is strong enough to keep water liquid on a planetary surface. That conception, which dominated thinking about habitability for most of the 20th century, has been dismantled by the outer solar system missions of the past 3 decades, replaced by something larger, something more complex, a solar system in which the potential for liquid water, and therefore the potential for life, is distributed across an enormous range of distances from the sun, wherever the internal heat budget of a world is sufficient to maintain a liquid layer. Triton contributed to that dismantling. Its geologically young surface, its active geysers, its thermal history, all of it added weight to the argument that the outer solar system is not a frozen graveyard, but a dynamic environment where geological and potentially biological processes are ongoing. But Triton's contribution to our understanding goes beyond the habitability question. It also tells us something profound about the history of the solar system itself. The 2024 study confirming that Triton and Pluto share the same chemical fingerprints, the same nitrogen, methane, and carbon monoxide proportions consistent with formation beyond the frost line in the same region of the outer solar nebula, is more than a piece of Triton's biography. It is evidence for the extraordinary violence and dynamism of the early solar system, a period when the giant planets were not in their current positions, when Neptune was migrating outward, scattering the population of the Kuiper Belt into new orbits. Triton's capture is a fossil of that era, a physical record, preserved in the retrograde orbit, the tidal heating history, the young resurfaced crust, of what the solar system looked like 4 billion years ago, when everything was still finding its place. And Pluto, Triton's chemical twin, tells the other side of that story. What a Kuiper Belt object looks like when it is not captured. When it remains in the outer solar system on its own trajectory, cold, slowly evolving, not subjected to the intense tidal heating that Triton experienced. New Horizons showed us Pluto in extraordinary detail. Its nitrogen plains, its mountain ranges, its haze layers, and seasonal atmosphere. A world that has evolved slowly and quietly in the outer solar system for 4.5 billion years. Triton is what Pluto would look like if it had been captured instead. Heated, geologically activated, its surface completely reshaped by the tidal energy of the planet that took it in. The comparison between the two, using the same generation of instruments on both, would be one of the most scientifically powerful observations in the history of planetary science. Voyager 2 saw Triton with 1989 technology. New Horizons saw Pluto with 2015 technology. The datasets are not directly comparable. A mission to Triton equipped with modern instruments would allow a true apples-to-apples comparison. Two worlds of the same origin, one that stayed free, one that was captured, examined with the same quality of instruments and the same analytical framework. The science that would emerge from that comparison alone, setting aside the ocean detection and the plume sampling, would reshape our understanding of how Kuiper Belt objects form and evolve. There is another lesson that Triton teaches, one that sits outside the domain of planetary science and touches something more philosophical. It is a lesson about time. Human history, recorded human history, covers roughly 5,000 years. The age of the universe is 13.8 billion years. Our entire recorded history is less than 4/10,000ths of 1% of the age of the universe. We are, in the most literal possible sense, newcomers. Triton was captured by Neptune 4 billion years ago. It spent at least 1 billion years as a global liquid ocean. Its surface was reshaped by geological processes less than 100 million years ago, before our ancestors were recognizably human. Its geysers have been erupting, continuously or intermittently, for timescales that dwarf the existence of our species. And it will continue its backwards orbit for another 3.6 billion years before Neptune finally destroys it. We exist, in Triton's timeline, as a brief flicker. A moment so short that if Triton's entire history from capture to destruction were compressed into a single calendar year, all of recorded human civilization would occupy less than 1 second of that year. And yet, in that 1 second, we have managed to launch a spacecraft that flew past Triton and returned images detailed enough to reveal its cantaloupe terrain and its active geysers. We have built telescopes sensitive enough to measure the chemical composition of a world 4.5 billion kilometers away. We have developed the theoretical framework to understand what those measurements mean, to infer the existence of a possible subsurface ocean from surface geology and thermal models. We have designed a mission that could confirm or deny that ocean. In the context of Triton's 4 billion year history, this is an almost incomprehensibly brief moment of awareness. A world that spent 4 billion years unknown to any intelligence, briefly in the span of a human lifetime. Becoming known, becoming understood, becoming the subject of scientific inquiry that may, within the lifetimes of people alive today, determine whether it harbors or has ever harbored life. The generation of scientists who will answer the Triton question, who will build and launch and operate the spacecraft that finally returns to Neptune and Triton with modern instruments, is almost certainly alive today. Some of them are already working in planetary science. Graduate students, postdocs, early career researchers who have grown up knowing about Triton's geysers and ocean potential and doomed orbit. Others are still in school, still discovering, for the first time, that the solar system contains worlds like this. Worlds that orbit backwards and erupt nitrogen geysers and hide possible oceans beneath frozen surfaces and spiral slowly toward destruction. Still having the reaction, the genuine, visceral reaction, of encountering something that seems impossible and discovering that it is not only possible, but real. That reaction, the feeling of the world becoming larger and stranger and more extraordinary than you thought it was, is the foundation of every scientific career that has ever contributed anything meaningful to human understanding. Triton provokes it, reliably, in everyone who encounters it properly, not as a name in a list of Neptune's moons, but as a world with a biography and a present and a future. And here, in this final chapter, is the thought that Triton's story leaves behind. There is a question at the heart of modern planetary science that Triton forces into sharp focus. Not the question of whether Triton has an ocean, though that is answerable, and we should answer it. Not the question of whether life exists or existed beneath its ice, though that too is worth every effort to answer. The deeper question: how many worlds like Triton are there? How many captured Kuiper Belt objects, scattered by Neptune's migration into encounters with planets, ended up in situations similar to Triton's, heated by tidal forces, kept liquid for geological timescales, possibly harboring chemistry or life in subsurface oceans that no telescope has ever been able to probe? And if Triton was, then in other planetary systems, around other stars, around ice giants orbiting at Neptune-like distances, captured large moons may be doing what Triton does, orbiting backwards, heated by their captors, hiding oceans in their interiors, erupting geysers from surfaces that should, by the simplest calculations, be completely frozen and dead. We cannot visit those worlds, not with any technology we possess or can foresee possessing. But we can visit Triton, and what we learn there about how captured moons evolve, about what their oceans contain, about whether the conditions they experienced were sufficient for life, will be the template for understanding every world like it that we will ever discover. Triton is not just a moon of Neptune. It is the nearest and most accessible example of an entire class of worlds that may be distributed across the galaxy. A class of worlds that we have only one opportunity to study up close, with instruments powerful enough to answer the questions that matter, before the orbital window closes for a generation. That opportunity exists right now, in the decisions being made about what missions to build and fund and launch in the next decade. 8. In the trajectory calculations that show a Jupiter gravity assist available in the early 2030s. In the careers of the scientists who have spent their working lives building the case, designing the instruments, calculating the trajectories, writing the proposals. Triton is asking a question. The question of whether it is alone in what it might be, whether its ocean, if it exists, is unique in the solar system, or one of many, whether the conditions it experienced after capture were sufficient, whether 4 billion years of liquid water in contact with warm rock, in the darkness beneath the ice, led anywhere. We are the first species in the history of this solar system capable of asking that question. And we are the first species capable of going to find out. The only question that remains is whether we will. The story is told. The questions are asked. and somewhere, 4.5 billion kilometers from where you are, Triton is still moving, backwards through its orbit, as it has moved for 4 billion years, without interruption, without deviation, patient in a way that nothing human has ever been patient. Above its frozen surface, Neptune hangs in the sky. Blue, still, 8 degrees wide, 16 times the size of our full moon, never rising, never setting, just there, suspended in a sky of perfect black and infinite stars, looking down at the frozen landscape below. On the surface, a thin nitrogen haze drifts at low altitude. Too thin to see, too thin to feel, but real, moving in its own slow patterns, carrying the faintest traces of what erupted from the geysers hours or days or years ago. And somewhere in the southern ice, another plume is building. Dark material warming under the translucent nitrogen ice. Pressure accumulating, waiting for the moment when the ice above gives way and another dark column rises into the sky. Let your body be heavy now. Let your breath find its own rhythm. Somewhere beneath Triton's ice, if the models are right, there is warmth, radiogenic heat, ancient and slow, the decay of elements that have been releasing energy since before the Earth existed. That warmth has been there for 4 billion years. It will be there for billions more, patient, constant, unchanging on any time scale a human mind can truly comprehend. Above the surface, the stars, undimmed by any atmosphere worth speaking of. The Milky Way, a solid river of ancient light across the black. Light that left its sources before human beings existed, before mammals existed, before anything on Earth had yet learned to see. Triton moves through all of it, backwards and slow and utterly indifferent to the passage of human time. Its orbit shortening, millimeter by millimeter, year by year, in a countdown that will not reach its conclusion for longer than life has existed on Earth. There is something steadying about that, about a world that carries its fate so calmly, that erupts and freezes and erupts again, that keeps its ocean, if it has one, hidden and warm in the dark beneath its ice, that orbits and orbits and orbits. You do not need to hold anything right now. The solar system will continue without your attention. Triton will keep moving. Neptune will keep watching. The geysers will keep building their pressure in the ice. The stars will keep their ancient light falling on a frozen surface that has never known warmth from above, only from below. Let your eyes be heavy. Let your thoughts move slowly, like the orbit of a distant moon, like the imperceptible decay of a captured world, like the patient warmth of radiogenic heat building in the dark. Far away, Triton turns, backwards, alone, extraordinary, going the wrong way, as it always has, as it always will. Good night.